let me tell you a little bit about calorimetry and thermodynamics. Okay, there's different ways to do calorimetry experiments. Basically, behind a calorimetry experiment is you're measuring a change in temperature somehow and relating that to the heat that's either being added or released as a reaction or a dissolving process is taking place. Okay, so there's a few ways to do these calorimetry experiments. One simple way, which sounds kind of cool actually, is something called a Bohm calorimeter. Okay, and so the way the Bohm works is things are done at a constant volume. There's also something called a coffee cup calorimeter, which doesn't really sound as exciting, but it's still a pretty cool experiment. This one is done at a constant pressure. Whether you're doing things with a Bohm or with a coffee cup calorimeter, we assume that the entire system is adiabatic. The word adiabatic just means perfectly well insulated, so that there's no heat transfer or heat lost between the system, which is the sample, and the surroundings, which is the outer part, maybe the water bath that things are dissolved in, or the metal casing. Okay, also another case, we're going to assume that the change in temperature in the calorimeter experiment is going to be proportional to the heat that it absorbs. Okay, and so in the case of a Bohm calorimeter, for example, Q is proportional to delta T, or if I want to make this an equality, I can say that Q is equal to C times delta T, where capital C is what's called the heat capacity of the calorimeter. Okay, so here I tried to show you a diagram of what a Bohm calorimeter looks like. So the idea is that on the outside you have a kind of metal casing. Inside you have some water to maintain the temperature at a certain value. There's a thermometer there so you can measure the temperature. And then inside this little rectangle in the center, that's where you plop your sample, which you usually just burn. Okay, so combustion takes place. You're going to add oxygen, gas from the outside, and you literally spark this. Okay, so there's like an electrical button you press, and combustion takes place. Whatever is in the sample is going to create carbon dioxide and water, typically if it's organic, and release tremendous amounts of heat energy, which means that the temperature is going to go up, so I can register that with my thermometer, and then based on whatever the change in temperature is from when I started the experiment to when I ended the experiment, I can then compare that or use that to calculate the Q, the heat, if I also know the heat capacity for this calorimeter. Okay, so let me give you an example. Let's say that you know the heat capacity for your Bohm calorimeter to be 5.15 kilojoules per degree Celsius. Then what you do is you take a little sample of graphite, which is an allotrope of carbon, and you place it in this Bohm calorimeter and use an excess of oxygen. Okay, so the water, the Bohm calorimeter, and everything else in here is all set to be at exactly 25.00 degrees Celsius. Okay, then you ignite the thing so it burns, and the water temperature goes up to 28.05 degrees Celsius. Okay, question is, let's figure out the change in enthalpy, or delta H, for this reaction. Okay, where I'm starting with graphite, carbon, and I'm adding oxygen to it, O2, to create CO2 gas. So the key to solving this problem is to realize that all of the heat that the calorimeter absorbed had to come from this combustion reaction. So what I can do is use the values that I was provided to find the heat that was absorbed by the calorimeter using the equation Q is equal to C times delta T. So for the calorimeter, I know that the heat capacity was given as 5.15 kilojoules per degree Celsius. Delta T is my change in temperature, right? So my initial temperature is 25.00 degrees Celsius. Final temperature was 28.05 degrees Celsius. So if I subtract these and then multiply by 5.15, I get 15.7 kilojoules. That's how much heat the calorimeter absorbed. If I look at it from the point of view of the reaction must have lost that amount. Okay, and so Q for the reaction is going to be negative 15.7 kilojoules. Remember, the minus sign is because heat is being released by the reaction. Positive for the calorimeter because it's absorbing that amount of energy. Okay, then, now what I can do is calculate the change in the internal energy, delta U or delta E, depending on the book you're using, for this combustion of 1 mole of graphite, because I want this to be in kilojoules per mole. Okay, and so I know that I had 0.480 grams of carbon, and that was responsible for an amount of energy equal to 15.7 kilojoules. So if I divide the negative 15.7 kilojoules by the 0.48 grams of carbon, that'll give me kilojoules per gram. And then if I multiply this by the molar mass of carbon, 12.011 grams per mole, this gives me negative 393 kilojoules per mole. So that means that my change in energy is negative 393 kilojoules per mole. I really wanted to find change in enthalpy, however. Okay, and so what I can do is say that for an ideal situation where it's isothermal, constant temperature, delta H is equal to delta U plus RT times delta N. Because the temperature change is pretty small, we can assume that it's pretty close to isothermal. Okay, the delta N is a change number of moles of gas. So in this case, I have 1 mole of gas on the product side and 1 mole of gas on the reactant side. 1 minus 1 is 0. So in this case, actually that whole term drops out anyway, and delta H is equal to delta U. So I can estimate that my change in enthalpy will be negative 393 kilojoules per mole. Okay. Let me tell you about another kind of calorimeter experiment, the coffee cup calorimeter experiment. Okay. Typically, you could literally use like a styrofoam coffee cup, but there are fancier versions of this. For example, something called an adiabatic flame combustion calorimeter, or differential scanning calorimeter, or isothermal titration calorimeter. All of these are going to be related to finding changes in enthalpy for the reaction. Good news is, for liquids and solids, changes in enthalpy and changes in internal energy are going to be pretty close to exactly the same because their volumes are pretty negligible, at least compared to that of gases. So here's what a coffee cup calorimeter looks like, very schematically. Okay, and so you can literally just take a styrofoam coffee cup and fill it with water. Okay, have some source of heat on the outside, and you have a thermometer inside to measure the temperature, as well as a mixer to make sure that everything is kind of stirring and dissolved properly. I'm going to plop my sample into here and record the changes in the temperature before and after the sample is added. So here's what this might look like. Okay, let's imagine that you took a sample of a metal alloy, okay, it's a chunk of metal that has a mass of 15.5 grams. And you heat this to a pretty high temperature, right, maybe 98.9 degrees Celsius. And then you plop it into this calorimeter where the water in the calorimeter is at a temperature initially of 22.5 degrees Celsius. And I measured the amount of water that I had in there to be 25.0 grams. Okay. After I let them kind of stir for a while, the temperature of the water rose from 22.5 to 25.7 degrees Celsius. So based on this information, let's try to calculate what the specific heat of this alloy is going to be. Okay, so the key to solving this problem is to realize that all of the heat that was lost by the hot metal alloy, the solid, had to be gained by the water in the cup. Okay, so let's figure out what the heat change is for the H2O, for the water. So I can say that Q for the water is equal to mc delta T, right? The mass times the specific heat, or heat capacity if you're doing moles, times change in temperature. So I know the mass of water is 25 grams. The specific heat of water is 4.184 joules per gram degree Celsius. This is a number that you'll be provided in a table, or they'll give it to you in the question itself. And the change in temperature is the final temperature minus the initial temperature. So once again, I started at 22.5 degrees Celsius. I ended at 25.7 degrees Celsius. So if I multiply everything out, I get 334 joules. That means that the heat gained by the water is equal to 334 joules. This has to be equal and opposite to the heat that the alloy lost. Remember the sign convention we talked about earlier. The alloy is losing energy, so that's going to be negative 334 joules. Okay, now that I know that, let's figure out the specific heat of the alloy. Use the same Q equals mc delta T formula, but now I'm going to use it in reverse. I'm going to solve for C, the heat capacity or specific heat. Okay, so C is equal to Q over m delta T. The Q we decided was negative 334 joules. The mass of the alloy is 15.5 grams. Delta T now is the change in temperature of the alloy. Okay, so 5.7 was the final temperature. Started out at a much higher temperature, right, 98.9 degrees Celsius. So notice that if I subtract 25.7 minus 98.9, this is a negative number, but I have a negative sign in the numerator for the heat. So those minus signs are going to cancel out, and I'll have a net positive number, which is what I want. Okay? So when I work this out, my heat capacity, or specific heat, I should say in this case, will be 0.29 joules per gram degree Celsius. Let me give you a final example. Okay. Earlier in this course, we talked about acid-base neutralizations. So let's say that you literally did one of these reactions. Okay. You had a solution of HCl, hydrochloric acid, which had a concentration of 0.25 molar. And you took 50 milliliters of that sample, and you reacted that with a solution of sodium hydroxide, NaOH. Same volume, same concentration, 50 milliliters, 0.25 molar. Also at the same temperature, they're both at 19.5 degrees Celsius. And I do this experiment in one of these coffee cup calorimeters. Okay, after they mix, the solution temperature went up to 21.21 degrees Celsius. Okay, so let's use this information to figure out what the heat is for this reaction, change in energy for this reaction. Okay, so helps to write down what the reaction is that's taking place. And again, this is the kind of overall reaction, neutralization of HCl and NaOH to give me sodium chloride and water. Now let's make a few assumptions and simplifications. Okay, let's assume that the volumes are additive because they're both aqueous solutions. So I can assume that the total volume is going to be the sum of the individual volumes that I started with. So I had 50 milliliters of my HCl solution and 50 milliliters of my sodium hydroxide solution. That's 100 milliliters total. Then I'm going to assume that any salt that I made is going to be a pretty small amount compared to how much water is present. So it's sufficiently dilute that the density of this kind of saltwater solution and the specific heat of the saltwater solution are going to be about the same as that for pure water. And so I'm going to assume that the density is about 1 gram per milliliter and that the specific heat is about 4.184 joules per gram degree Celsius. Then, just like before, we're going to assume that the system is adiabatic, so it's perfectly insulated. There's no heat lost from the calorimeter. And we're also going to assume that the heat required to warm any part of the calorimeter is negligible other than from this sodium chloride solution. So if you're willing to buy all of those assumptions and simplifications, you can basically solve this problem. Okay, so let's figure out how much heat is being absorbed or retained by the calorimeter. Okay, and so this is going to be my Q equals mc delta T formula. But now for the mass, I'm just going to replace that by the density and the volume. Okay, and so I know that density rho is equal to mass over volume. So if I just cross multiply, the mass is equal to the density multiplied by the volume. Okay, and so I know that the volume is 100 milliliters. The density, I'm assuming, is 1 gram per milliliter for water. Here's my specific heat of water, 4.184 joules per gram degree Celsius. Here's my change in temperature for the solution, which I assume is that of water, 21.21 minus 19.50. This gives me 715 joules. So that's how much heat the calorimeter gained. Now, if I look at it from the point of view of the reaction, right, the reaction must have lost this much energy to give it to the calorimeter. So Q for the reaction is minus Q for the calorimeter. So that's going to give me negative 715 joules. Good way to remember this is if the reaction is losing energy, okay, it's exothermic. It's giving that energy to the surroundings. The surroundings get hot. Okay, and so for exothermic reactions, temperature goes up and your Qs are negative. For endothermic reactions, they're absorbing energy from the outside. Okay, and so the temperature of the outside is going to go down, but your Q is going to be positive because that's being absorbed.